Hello everybody. Today I'm going to explain the solution to the second problem from the 2025 USACO January contest in Silver Division, the problem 2 Farmer John's favorite operation. In this problem, we are given an array of n integers as well as an integer m, and in one operation we can uh, pick an index I and subtract or add 1 to a of I. And based on Farmer John's question on an integer x, we want to find the minimum boredom value we would have, which is the minimum number of operations to make sure that ai minus x is divisible by m for all values from 1 to n. And among all possible x's, we want to find the minimum possible boredom value. And as you can see, we are given a lot of test cases, and n can go up to 200,000 in each test case. And now we want to find out a way to compute this boredom value pretty fast. Now, obviously, a brute force scenario we can use is that given that m is small for at least the input 2, we can try every single remainder when dividing by m, because this part from here, ai minus x being divisible by m, is equivalent to ai having a remainder of x when dividing by m. And now what we can do is that we can, for example, try every single remainder and see how long it would take us to reach out to that remainder, and this would be good enough to get the input 2. Now, the question is, how do we improve this method further? And as you can see, if we look by the distribution of the subtasks, the idea for the full solution is a very big step from the brute force ideas to the entire solution. So we need to think at a way to compute these answers fast. Now, one thing I did when I solved this problem was to start from what happens when we have a single value. And if we have a single value, and let's say that we will first compute the remainders when dividing by m. But if we have a single value, let's say 5, and m is 21, let's say that m is a larger number, and then we want to find the number of ways to arrive to a certain remainder. And if we plot the answers for various remainders, so for 5, the chart would look like this. So we would start from 5. So if we go from 0, we would have 0, 5, and let's say 15 and 20 as remainders. 20 as remainder. And at position 0, we will need 5 operations. So if we plot this on a 2D chart, so the beginning, the answer would be 5. So from here, and this would be 0, and this would be, let's say, 10. And if we go from, this value here, the answer would decrease linearly up to the minimum point. When we have 5, then the answer would become 0, because we already have a remainder of 5 and we don't need any moves to get there. However, the answer would slowly increase until we get to a remainder of 15, where we will need 10 operations to get there. Getting to a remainder of 16 would also require 10 operations, because we go downwards from 5 to 0, and then from 0 to 16 by 5 more operations. So we would have a plateau here for exactly one move. And then after this point, we would steadily decrease down to 20, when the answer would become 6. So if we go by this sort of technique, for example, this problem, when I solved it, and when I tried to compute this sort of plots on my paper, and also here it reminded me a lot of various experiments I would do in some physics class in the middle school. But even without that physics background, we can still deduce that we care a lot about the main relevant points. And uh, here I mentioned the uh, top answers, the most relevant answers, and also the final one. And now if we look at these lines, here we have two decreasing lines. So we have here two -1 direction lines and a positive increase line, so +1. And now we can observe that throughout the entire interval from 0 to m-1, the direction only changes a few times. And possibly if we have an odd m, we could get a flat position where everything stays the same for one move. Now, this idea, when I went and explored further, I remember that it's actually not that dissimilar with what I did for the problem teleportation, the problem from the 2018 February contest in the silver division. I will also link the video for teleportation in description because a lot of the ideas you will see that they are very similar with that problem. So again, you will see that for this problem, it's also another reason why you should practice all past USACO problems, even those which are old and seem old-fashioned. And this is what helped me a lot here also, because if we look at it, we can think at performing some sort of difference arrays, but not on the actual values, not on the actual answers, but more like on the slope of changes. So here we could have a difference, we could have an entry in our difference array. We would start with, let's say, something like the difference of 0 decreasing. Then here at position 5, we need to change entirely the slope and make it +1. How do we do this? We need to add 2, because we need to neutralize the decrease as well as add an increase. Then here at this peak position at 15, we need to subtract 1. Why not 2? Because for one more position, we have the same value. And if we do it, then we can now compute the rate of change for all values. Now, there might be cases in which if we have a bigger remainder, then the answer would still require more moves. For example, if we were to do it for another remainder, let's say something like 13. So for something like 13, here at the beginning we would have 8. So for example, we would have, let me plot this again. So for example, at the beginning we would have 8, because we can go in 8 operations from 0 to 13. Then here we would have the peak, which is 10, which goes for one more position. Then it will slowly come down until here, where we have 13. And then at the end, we would have 7. And this would give us the chart for this position. So again, it depends a lot on the kind of value we have. Let me color it differently to make it maybe easier to observe, or not. And again, we have -1s and the plot segment, and also the +1s. And again, how do we turn these from some fancy looking charts to, let's say, the actual answer? Now, for all of these points from here, we can add the information on these different arrays in a map. And then, just like in teleportation, we need to keep track of the sum of slopes and also the sum of changes. And we need to start by computing using brute force the sum of changes required to get to 0. And after doing this, you will see also when I show you the implementation that it's very similar with what we had for teleportation. So again, you will see exactly what I meant there. And if we look at these, if we look at the code here, I had two functions for the positive and negative delta. And here, because I had bugs initially, I generated myself a test case using a test case generator, where I just plugged in the brute force solution. And this test was very important towards helping me figure the bugs, because I had some major bugs in the code, and using this test case was all I needed to fix them. And here, as you can see, I compute the number of operations for 1 and 0. In case I have the flat spot at the beginning, I just delay everything by 1. And then I have a bunch of casework depending on whether I have a greater value at the beginning or a smaller value at the beginning, because I needed to adjust the difference arrays, as you can see. And here we add, we subtract, then depending on whether we have the flat spot, we subtract again at that point or later, and we add 2 in case we go back to the positive. So again, very important here, it was very important here to make sure that when you compute this, you have a clear idea of what you need to add and where you need to add them. Using some drawings or performing other sort of calculations, or even just storing all the answers from 0 to n-1 can all be very helpful steps in that regard. And then after I did this, if m is 1, a corner case, I printed 0. Otherwise, I kept the sum of deltas and the sum of the previous value, because I wanted to make sure that I avoid any sort of let's say corner cases or mistakes in that regard. Again, this part is very similar to what I did in teleportation as well, and then I just print the answer at the end. As you could see, in this problem, I combined some ideas I had from having solved teleportation and actually made a video out of it, and with some knowledge of difference arrays and checking exactly the way we can plot these answers on some charts. And then from there, it turned into a rather tedious exercise on difference arrays and on clean implementation. Both skills were very important towards solving this problem. And then after doing these things, as you can see, I had a few bugs at the beginning until I ran this, and then I got the full result. As the input size is rather big, so you need to be careful at adding your fast input methods from your programming language as well. If you enjoyed watching this video, please like the video and subscribe to the channel. And if you have any sort of feedback or suggestions, please leave them in the comments and share this video with your friends or with anyone else who is interested in learning how to solve USACO problems from the highest quality source out there. In addition, if you or someone else is interested in working more closely with me, you can check out my links in the descriptions for ways to join my tutoring program in order to benefit from the best expertise in the field. Until the next time, please check out the other videos I made on the channel on bronze and silver problems. And good luck with the future USACO contests. And if you have any sort of question, I am waiting for them in the comments. Good luck and see you next time. Bye.